I want you to do something. I want you to step outside, away from the glow of your phone, away from the streetlights, away from everything that hums and buzzes in your daily life. Find a dark patch of sky. Look up and just breathe. Let your eyes adjust. Let the stars come into focus, one by one, then dozens, then hundreds, until the sky looks like someone scattered diamonds across black velvet. What you are seeing with your naked eyes right now is roughly 4,500 stars. That sounds like a lot. It is not. That number, 4,500, is so small compared to what is actually out there that it is almost meaningless. It is like scooping a cup of water from the Pacific Ocean and saying you have seen the sea. Our galaxy, the Milky Way, the band of hazy light you might see stretching across the sky on a truly dark night, contains somewhere between 200 billion and 400 billion stars. Let me say that again because the human brain is not wired to understand numbers this large. 200 billion to 400 billion stars in one galaxy. And our galaxy is not special. It is not particularly large. It is, by cosmic standards, completely ordinary. The observable universe, the part of the universe whose light has had time to reach us since the Big Bang 13.8 billion years ago, contains approximately 2 trillion galaxies. 2 trillion, each with hundreds of billions of stars. When you multiply all of that together, you arrive at a number so large, it almost loses meaning. Roughly 70 sextillion stars. That is a 7 followed by 22 zeros. 70,000 billion stars. And around those stars orbit planets. As of right now, NASA has confirmed the existence of more than 6,000 exoplanets, planets orbiting stars other than our Sun. But that number represents only what we have managed to detect with our current technology, which is limited and biased toward finding large planets close to their stars. The real number of planets in our galaxy alone is estimated to be in the hundreds of billions. Some models suggest there could be 40 billion Earth-sized planets sitting in the habitable zones of their stars, just in the Milky Way, 40 billion worlds where liquid water could potentially exist on the surface. 40 billion chances for something to stir in the chemistry of a warm ocean. 40 billion rolls of the dice. So here is the question that has haunted scientists, philosophers, and anyone who has ever looked up at the stars and felt the weight of their own smallness. With all of those stars, all of those planets, all of that time, 13.8 billion years of cosmic history, billions of years before our sun even formed, where is everybody? Why, when we point our most sensitive instruments at the sky, do we hear nothing? Why, when we scan the electromagnetic spectrum for any hint of artificial signal, any signature of technology, any evidence that someone somewhere built something, do we find only natural noise? Why, in over 6 decades of dedicated searching, has humanity found not a single confirmed sign of intelligent life anywhere in the observable universe? The silence is not just disappointing. It is, when you truly sit with the numbers, deeply and profoundly disturbing. Because the math says the universe should be buzzing with life. The math says we should have been visited long ago. The math says the evidence should be overwhelming and obvious and everywhere. And yet there is nothing, just silence. An enormous, echoing, absolute silence that stretches from one end of the cosmos to the other. And tonight, we are going to explore the most chilling explanation for why that silence exists. We are going to follow the evidence, step by step, from the very first moment this question was asked to the cutting edge of modern science. We are going to look at every angle, examine every piece of data, and confront every uncomfortable possibility. And by the end, you may never look at the night sky the same way again. Before we go any further, if this is the kind of deep, reality-based exploration that fascinates you, take a second right now to hit that subscribe button and drop a comment below telling me what you think. Do you believe we are alone in the universe? Hold that thought, because the answer might be more complicated and more terrifying than you expect. Let us begin at the beginning. The year is 1950. The place is Los Alamos, New Mexico, a small town perched on a mesa in the desert. A town that just 5 years earlier had been the secret heart of the Manhattan Project, where the first atomic bombs were designed and built. The echoes of Hiroshima and Nagasaki are still fresh. The Cold War is intensifying, and the scientists who work here, some of the most brilliant minds in the history of physics, are wrestling with questions about the nature of the universe and humanity's place in it. On a summer day in 1954, physicists are walking to lunch at the Fuller Lodge. Their names are Enrico Fermi, Emil Konopinski, Edward Teller, and Herbert York. Fermi is the most famous of the group, a Nobel Prize-winning physicist who had predicted the existence of the neutrino, helped create the first artificial nuclear reactor, and played a central role in the development of the atomic bomb. He is known among his colleagues for something particular, a habit of posing deceptively simple questions that seem almost childish on the surface, but contain depths that can occupy a brilliant mind for days. These are called Fermi questions. How many piano tuners are there in Chicago? How many atoms of Caesar's last breath do you inhale with each lungful of air? Questions that seem unanswerable, but can be approximated with clever reasoning. As the four men walk, their conversation drifts to a topic that is very much in the air in 1950. Flying saucers. Reports of unidentified flying objects have been making headlines, and the physicists are discussing, partly seriously and partly in jest, whether faster-than-light travel might be possible, and whether Earth might be receiving visitors from other worlds. They laugh, they speculate, they arrive at the lodge, sit down to eat, and the conversation moves on to other subjects. And then, seemingly out of nowhere, in the middle of an entirely different discussion, Enrico Fermi looks up and blurts out a question. The exact words are remembered slightly differently by each person present. Edward Teller recalled it as, "Where is everybody?" Herbert York remembered it as, "Don't you ever wonder where everybody is?" Emil Konopinski recalled, "But where is everybody?" The specific wording does not matter. What matters is what happened next. According to Teller, the result of his question was general laughter because of the strange fact that, in spite of Fermi's question coming out of the blue, everybody around the table seemed to understand at once that he was talking about extraterrestrial life. There was no need to explain, no need to provide context. Every physicist at that table instantly grasped the weight of the question. If the universe is so vast and so old, if the conditions for life are even remotely common, if other civilizations have had millions or billions of years of head start on us, then where are they? Why haven't they shown up? Why haven't we found any trace of them? Herbert York later recalled that Fermi followed up his question with rapid back-of-the-envelope calculations, the kind of quick mathematical reasoning he was famous for. He estimated the probability of Earth-like planets, the probability of life arising, the likelihood of intelligent life developing, the probable duration of technological civilizations, and he arrived at a conclusion that disturbed everyone at the table. Based on those calculations, Fermi concluded that Earth ought to have been visited long ago and many times over. The math worked out, the logic was airtight, the conditions existed, the time was sufficient, and yet no visitors had come, no signals had been received, no artifacts had been found. Something was wrong, either with the assumptions or with reality. That question, born over lunch at a weapons laboratory in the New Mexico desert, would come to be known as the Fermi Paradox, and it has remained one of the most important unanswered questions in all of science for over 70 years. Now, to truly feel the force of this paradox, you need to understand why the silence is so mathematically bizarre. Let me walk you through the logic slowly, because every step matters. Our sun is roughly 4.6 billion years old. That sounds ancient, and by human standards it is. But the universe is 13.8 billion years old. That means the universe was already 9 billion years old when our sun formed. 9 billion years. Stars were forming, planets were coalescing. Chemistry was happening for 9 billion years before Earth even existed. Many of the stars in our galaxy are significantly older than our sun. Some are 10 billion years old, 11 billion years old. Their planets have had 5 or 6 billion more years than Earth to develop life. 5 or 6 billion extra years. Now think about what humanity has accomplished in the last 10,000 years since the agricultural revolution. We went from farming with sticks to landing on the moon, building particle accelerators, and sending robotic probes beyond the edge of our solar system. In just 10,000 years. In the last 200 years alone, we went from riding horses to splitting atoms. In the last 100 years, we developed radio, television, radar, computers, the internet, nuclear weapons, spacecraft, and telescopes that can see 13 billion light years into the past. 100 years. Now imagine a civilization that had a head start of not 100 years, not 1,000 years, not 1 million years, but 1 billion years? What would they be capable of? What technologies would they possess that we cannot even conceive of? This is not science fiction speculation. This is a straightforward mathematical observation. Such civilizations should statistically exist. And here is the key point that makes the paradox truly sharp. You do not need faster-than-light travel for a civilization to colonize the entire galaxy. Even with slow, plodding, sub-light-speed ships, the kind that are almost within the reach of our own technology, a civilization could spread across the entire Milky Way in 5 to 50 million years. That sounds like a long time. It is not. 50 million years is just 0.36% of the age of the universe. It is a cosmic blink. It is less than the time since the dinosaurs went extinct. If even one civilization, anywhere in the galaxy, at any point in the last several billion years, had developed the ability and the will to spread among the stars, the evidence should be everywhere. Their probes should be in our solar system. Their signals should be detectable. Their megastructures should be visible. The galaxy should be colonized. And yet it is not. The silence is total. The evidence is zero. Something is preventing this from happening. Something is filtering out civilizations before they reach that stage. And figuring out what that something is may be the most important question humanity has ever asked. Because if that filter lies ahead of us, rather than behind us, it means we are in mortal danger. In 1961, 11 years after Fermi's lunchtime question, an astronomer named Frank Drake organized the first scientific meeting dedicated to the search for extraterrestrial intelligence. It was held at the National Radio Astronomy Observatory in Green Bank, West Virginia, and only 10 scientists attended. Among them was Carl Sagan, who would go on to become one of the most famous science communicators in history. Drake wanted to give the meeting some structure, some framework for thinking about the problem systematically. So he wrote an equation on the blackboard. It was not a mathematical proof. It was not a formula that could be solved. It was a way of organizing our ignorance, a framework for identifying exactly what we do not know. The equation looked like this. N equals R star times F sub P times N sub E times F sub L times F sub I times F sub C times L. Each symbol represents a different factor that determines how many detectable civilizations should exist in our galaxy right now. R star is the rate at which new stars form in the Milky Way. This is something we can actually measure. The answer is roughly 1.5 to 3 new stars per year. So far, so good. F sub P is the fraction of those stars that have planetary systems. In Drake's day, this was unknown. We did not know if planets were common or rare. Today, thanks to missions like Kepler and TESS, we know the answer. Planets are ubiquitous. Nearly every star has at least one planet. The fraction is somewhere above 0.9. Almost all stars have planets. N sub E is the average number of those planets that can potentially support life, planets in the habitable zone with the right size and conditions. Based on current data, this is estimated at roughly 0.2 to 0.5, so maybe 1 in 5 stars has at least one potentially habitable planet. Still, these are encouraging numbers, but now we reach the boundary between what we know and what we do not know, and this is where everything falls apart. F sub L is the fraction of potentially habitable planets where life actually develops. We have absolutely no idea what this number is. Life appeared on Earth relatively quickly, within about 500 million years of conditions becoming stable, which might suggest that life arises easily wherever conditions allow. But we have a sample size of exactly 1. We cannot draw statistical conclusions from a single data point. This number could be close to 1, meaning life is almost inevitable. Or it could be astronomically small, 1 in a billion, or 1 in a trillion, meaning Earth is a staggering fluke. We simply do not know. F sub I is the fraction of life-bearing planets where intelligent life evolves. Again, we have no idea. On Earth, life existed for nearly 4 billion years before anything resembling human-level intelligence appeared. Bacteria ruled the planet for most of its history. Intelligence might be an incredibly rare evolutionary outcome, or it might be an inevitable consequence of sufficient time and complexity. We do not know. F sub C is the fraction of intelligent civilizations that develop technology capable of releasing detectable signals into space, things like radio transmitters or other electromagnetic technology. Not all intelligent species might develop such technology. Dolphins are intelligent. Octopuses are intelligent. Neither has built a radio telescope, and L is the length of time such a civilization remains detectable. This might be the most important and most uncertain term of all. A civilization might broadcast signals for 10 years, or 10,000 years, or 10 million years, or it might destroy itself within a century of developing advanced technology. Here is the problem. The first three terms of the Drake equation are now reasonably well constrained by observational data. We know that stars form regularly, that planets are common, and that many of those planets are in habitable zones. The numbers are encouraging, but the last four terms, the ones that deal with life, intelligence, technology, and survival, are completely unknown. And I do not mean slightly uncertain. I mean they span hundreds of orders of magnitude. When the 10 scientists at the Green Bank meeting in 1961 plugged in their best guesses, they arrived at estimates ranging from 1,000 to 100 million civilizations in our galaxy alone. Those are optimistic numbers. If they are right, the galaxy should be a crowded, noisy place. But other scientists, using more conservative estimates, have arrived at numbers far less than one per galaxy. This enormous range of possibilities means the Drake equation, while a brilliant conceptual tool, cannot by itself resolve the Fermi Paradox. It can only sharpen the question. In 2018, 3 researchers at the Future of Humanity Institute at Oxford University published a paper that changed the way many scientists think about this problem. Their names were Anders Sandberg, Eric Drexler, and Toby Ord, and their paper was titled Dissolving the Fermi Paradox. What they did was simple in concept, but revolutionary in execution. Instead of plugging single best guess numbers into the Drake equation, as everyone before them had done, they treated each unknown parameter as a range of possibilities, and used proper probability distributions. They acknowledged our true depth of ignorance. And when they ran the numbers this way, accounting for the real uncertainty in each term, they found something remarkable. There was a substantial probability, somewhere between 38 and 85%, that humanity is the only technological civilization in the entire observable universe. Not just our galaxy, the entire observable universe. 2 trillion galaxies, 70 sextillion stars. And we might be the only ones. This was not a fringe result from pessimistic cranks. This was a rigorous mathematical analysis published by respected researchers at one of the world's top universities. And it suggested that the Fermi Paradox might not be a paradox at all. The silence might be exactly what we should expect if we properly account for how much we do not know. But the story does not end with mathematics. To truly understand why we might be alone, we need to look at what we have actually done to search for other civilizations, and what those searches have found. Because humanity has not just been sitting around wondering, we have been actively looking for over 60 years, with increasingly powerful technology, and the results are sobering. The first serious attempt to detect alien radio signals was called Project Ozma. It was conducted by Frank Drake himself in 1960, 1 year before he wrote his famous equation. Drake pointed the 85-foot radio telescope at Green Bank toward 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for 150 hours. He was looking for narrow-band radio signals, the kind that natural processes do not produce, the kind that would indicate deliberate transmission by an intelligent civilization. He found nothing. No signals, no patterns, just the natural hiss of the cosmos. Project Ozma was crude by modern standards, limited in frequency range and sensitivity, but it was a beginning, and it established a pattern that would repeat again and again over the following decades. We look, we listen, we find nothing. Throughout the 1960s and 70s, other searches were conducted, each more sophisticated than the last. The Ohio State University operated a radio telescope called Big Ear from 1963 to 1998, scanning the sky continuously for anomalous signals. On August 15, 1977, Big Ear detected something that became the single most famous event in the history of the search for extraterrestrial intelligence. A volunteer astronomer named Jerry Amon was reviewing the telescope's data printouts when he noticed a signal that made his jaw drop. It was a strong narrowband signal at 1420 MHz. which is the emission frequency of neutral hydrogen, the most abundant element in the universe, and the frequency many scientists had long speculated an intelligent civilization might use to communicate. The signal lasted 72 seconds, which was exactly the duration you would expect for a point source passing through Big Ear's beam as the Earth rotated. It was strong, it was narrow, it was at the right frequency, and it came from the direction of the constellation Sagittarius. Eamon circled the signal on the printout and wrote a single word in red ink: wow. The wow signal, as it came to be known, electrified the SETI community. Here, finally, was something that looked like it could be artificial, but there was a problem. Despite hundreds of follow-up observations pointed at the same patch of sky, the signal was never detected again. Not once. An artificial signal from a persistent civilization should be repeatable. This one was not. For decades, the wow signal remained unexplained, tantalizing, hovering between the possibility of alien contact and the probability of natural origin. Then, in recent years, the mystery began to unravel. Research published in 2024 and 2025 provided strong evidence that the wow signal was likely a natural astrophysical event, probably caused by cold interstellar hydrogen clouds excited by a powerful energy source. A 2025 analysis even found that the signal was stronger than originally thought, but the natural explanation held firm. The signal that gave us our greatest moment of hope was almost certainly not what we wanted it to be. After the wow signal, the search continued and expanded. Project Phoenix, run by the SETI Institute from 1995 to 2004, was the most comprehensive targeted search of its time. It examined roughly 800 nearby stars across a wide range of radio frequencies. The result was the same: nothing. No artificial signals detected. Then came SETI at Home, launched in 1999, a groundbreaking project that used the idle processing power of millions of personal computers around the world to analyze radio telescope data. Over its 2-decade lifespan, SETI at Home processed an enormous volume of data and identified approximately 12 billion candidate narrowband signals. These were gradually winnowed down. 12 billion became millions. Millions became thousands. Thousands became hundreds. The project officially stopped distributing new data in 2020, but the analysis of the final candidates continued. The last 100 most promising signals are still being followed up. As of now, none have been confirmed as artificial. 12 billion candidates. 0 confirmations. The most ambitious SETI project currently operating is Breakthrough Listen, launched in 2015 with $100 million in funding from Russian-Israeli billionaire Yuri Milner. Breakthrough Listen is surveying 1 million nearby stars and the centers of 100 nearby galaxies using some of the most powerful radio telescopes on Earth, including the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia. It is the most comprehensive and sensitive search for technosignatures ever undertaken, and its results, published in multiple peer-reviewed papers, have been consistent. No confirmed detections of artificial signals. In a recent study, Breakthrough Listen examined data from 27 confirmed and candidate exoplanets identified by NASA's TESS mission, specifically looking for radio transmissions during planetary transits, when a planet passes in front of its star, and any signals from that planet might be most detectable. The result was, again, silence. In 2025, the SETI Institute published a study that offered a possible explanation for why we might be missing signals, even if they exist. The research showed that turbulent plasma in the stellar environments around distant stars could blur ultra-narrow radio signals before they leave their home star systems, making them undetectable by our instruments. This was a significant finding because it meant our searches might have a fundamental technological blind spot. We might not be able to detect certain types of signals, even if they are being actively transmitted. But this cuts both ways. It explains why we might not hear anything, but it does not confirm that anyone is actually transmitting. The silence remains, even if its interpretation has become more nuanced. Meanwhile, our ability to study exoplanets directly has undergone a revolution. The James Webb Space Telescope, launched in December 2021 and fully operational since 2022, is the most powerful space telescope ever built. One of its key capabilities is the ability to analyze the atmospheres of exoplanets, through a technique called transit spectroscopy. When a planet passes in front of its star, starlight filters through the planet's atmosphere, and different molecules in that atmosphere absorb different wavelengths of light. By studying which wavelengths are missing, scientists can determine what the atmosphere is made of. JWST has already detected carbon dioxide, water vapor, sodium and potassium in the atmospheres of several gas giant exoplanets. These are natural chemical detections, not signs of life, but they demonstrate the telescope's power. The most exciting and controversial JWST result came in April 2025, when a team of researchers announced they had detected possible biosignature gases on an exoplanet called K2-18b, a large planet located 124 light-years from Earth. K2-18b orbits in the habitable zone of its star and is classified as a Haitian world, a hypothetical type of planet with a hydrogen-rich atmosphere and a liquid water ocean. The team reported detecting dimethyl sulfide, a gas that on Earth is primarily produced by living organisms, specifically by marine phytoplankton. The announcement made headlines around the world. Had we found evidence of alien life? The excitement lasted about a week. By late April 2025, independent analyses using the same JWST data cast serious doubt on the detection. The signal attributed to dimethyl sulfide was faint and could be explained by other factors, including instrumental noise and alternative atmospheric chemistry. The scientific community largely concluded that the evidence was not yet convincing. The universe had teased us again and pulled away. This pattern, hope followed by disappointment, has repeated so many times in the history of astrobiology that it has become almost a ritual. We find something that might be life, we investigate further, and it turns out to be something else. Every time. Beyond radio searches and atmospheric analysis, we have also directly explored our own solar system with robotic spacecraft, and the results have been equally discouraging in terms of finding evidence of other intelligence. Every planet in our solar system has been visited by at least one probe. We have landed on Mars multiple times. We have sent spacecraft past every major body from Mercury to Pluto and beyond. We have examined the moons of Jupiter and Saturn in considerable detail. Nowhere have we found any artifacts, structures, probes, mining evidence, or any other indication that an alien intelligence has ever visited our solar system. The Hart-Tipler conjecture, formulated by physicist Michael Hart and mathematician Frank Tipler, states that if technologically advanced civilizations existed elsewhere in the galaxy, they would by now have sent self-replicating probes, called von Neumann probes, to every star system in the Milky Way. Such probes, even traveling at a small fraction of the speed of light, could explore the entire galaxy in a few million years. The fact that we have found no such probes in our solar system, after careful observation, is taken by some scientists as evidence that such civilizations simply do not exist. So let us take stock of where we stand. We have been searching for over 60 years. We have scanned thousands of stars at radio frequencies. We have analyzed billions of candidate signals. We have examined dozens of exoplanet atmospheres. We have explored our own solar system from one end to the other. We have the most powerful telescopes ever built, including space-based observatories that can peer billions of light years into the cosmos. And we have found nothing. Not a whisper. Not a trace. Not a shadow of evidence that anyone else is out there. The silence is real. It is measurable. It is documented. And it demands an explanation. Now we arrive at the heart of this exploration. The explanations, the hypotheses that scientists have proposed to account for the Great Silence. Some of these are reassuring. Some are unsettling. And some are genuinely terrifying. I want to walk through each of them carefully, examine the evidence for and against, and then, at the end, bring them all together into a single, coherent picture that I believe represents the most chilling answer to the question of why we appear to be alone. Let us begin with the most fundamental possibility. What if life itself is extraordinarily rare? What if the conditions required for life to arise from non-living chemistry are so specific, so demanding, so improbable that it almost never happens? This is the first, and perhaps most important candidate for explaining the silence. To understand why, you need to understand what it takes to create a living organism from scratch. The process is called abiogenesis, the emergence of life from non-life, and it is one of the deepest unsolved problems in all of science. Here on Earth, life appeared remarkably early in our planet's history. Earth formed about 4.6 billion years ago. For the first several hundred million years, conditions were hellish. The surface was molten. The planet was being bombarded by asteroids and comets during a period known as the Late Heavy Bombardment, which ended roughly 3.8 to 4 billion years ago. Almost immediately after the bombardment subsided, within perhaps a few 100 million years, the first microbial life appeared. The oldest confirmed fossils of single-celled organisms date to about 3.5 billion years ago, and chemical evidence suggests life may have existed even earlier, perhaps 3.8 billion years ago or more. This rapid appearance of life on Earth has led many scientists to conclude that abiogenesis must be relatively easy, that wherever conditions are right, life springs into existence quickly. But this reasoning contains a subtle and dangerous logical trap. We have a sample size of 1, Earth. We cannot determine the probability of an event from a single occurrence. Consider an analogy. Imagine you walk into a casino, and on your very first pull of a slot machine, you hit the jackpot. You might conclude that slot machines are easy to win, but that conclusion would be wildly wrong. The fact that you won on your first try tells you nothing about the actual odds, because you would not be standing there telling this story if you had not won. You only exist as a storyteller because the improbable event happened. This is called selection bias, or in a more formal context, the anthropic principle. We can only observe a universe in which life arose on our planet, because if life had not arisen, we would not be here to observe anything. The fact that life appeared quickly on Earth could mean abiogenesis is easy, or it could mean Earth was incredibly, spectacularly lucky. And we have no way, based on a single example, to tell the difference. The scientific challenge of understanding abiogenesis is enormous. Despite more than 70 years of intensive research, no one has ever succeeded in creating life from non-living matter in a laboratory. The famous Miller-Urey experiment in 1953 showed that amino acids, the building blocks of proteins, could form spontaneously from simple chemicals under conditions simulating early Earth's atmosphere. This was a landmark result. But amino acids are not life. They are ingredients. The gap between amino acids and a self-replicating cell is immense, like the gap between a pile of bricks and a functioning city. A living cell, even the simplest one we know of, is a staggeringly complex molecular machine. It contains DNA or RNA for information storage, proteins for carrying out chemical reactions, a membrane to separate its internal chemistry from the outside environment, and an energy metabolism to power its processes. How all of these components came together for the first time in the right configuration, in the right environment, at the right moment, is a question that remains unanswered. The RNA world hypothesis suggests that RNA molecules, which can both store information and catalyze chemical reactions, might have been the first self-replicating entities, predating both DNA and proteins. This is a promising idea, but the spontaneous assembly of functional RNA molecules from random chemistry faces its own probability challenges. Some estimates of the probability of abiogenesis range from near certainty on any habitable planet to less than 1 in 10 to the 40th power per planet per billion years. That range spans tens of orders of magnitude. We are not slightly uncertain about this. We are profoundly, catastrophically ignorant. And if the true probability of abiogenesis is at the low end of those estimates, then life on Earth is a cosmic miracle, an event so unlikely that it may have happened only once in the entire observable universe. The silence would be explained immediately. There is no one else, because the chemistry that produced us almost never produces anything. But let us suppose, for the sake of argument, that abiogenesis is not as rare as the pessimistic estimates suggest. Let us suppose that simple microbial life does arise on many planets wherever conditions allow. Even then, the path from simple life to complex life is not guaranteed. In fact, when you look at the history of life on Earth, one particular transition stands out as potentially the most difficult and improbable step in the entire chain: the emergence of eukaryotic cells. For the first 1.5 to 2 billion years of life on Earth, all living organisms were prokaryotes, simple single-celled organisms without a nucleus. Bacteria, and archaea. They were successful, they were diverse, and they were everywhere, but they were fundamentally limited in their complexity. They could not form multicellular organisms. They could not develop tissues, organs, or brains. They were stuck at a level of organization that, while remarkable in its own right, could never produce technology or civilization. Then, roughly 2 billion years ago, something extraordinary happened. An archaeal cell engulfed a bacterium, and instead of digesting it, the two organisms formed a permanent partnership. The engulfed bacterium became the mitochondrion, the energy-producing organelle that powers virtually all complex life on Earth. This event, known as endosymbiosis, gave rise to the eukaryotic cell, a new kind of cell with a nucleus, internal membranes, and vastly greater capacity for complexity. And here is the crucial point. This event appears to have happened exactly once. Not twice, not many times, once. In 4 billion years of life on Earth, with trillions upon trillions of interactions between prokaryotic organisms, the specific endosymbiotic event that produced eukaryotes occurred a single time. Every eukaryotic organism alive today, every plant, every animal, every fungus, every protist, traces its ancestry back to that one event. Research published between 2022 and 2025 continues to confirm that eukaryogenesis is widely viewed by biologists as an improbable evolutionary transition. A 2022 study published in Frontiers in Microbiology described the emergence of the eukaryotic cell as the emergence of an emergent superorganism, emphasizing just how extraordinary and unlikely the event was. A 2025 paper in Nature examined dated gene duplications to elucidate the evolutionary assembly of eukaryotic complexity, confirming that the transition involved a cascade of unprecedented innovations that happened in a remarkably specific sequence. If eukaryogenesis is as rare as it appears to be, then the universe might be full of bacteria. Microbial life might be common, coating the warm rocks of a billion worlds, filling subsurface oceans, drifting in alien atmospheres. But none of it would ever become complex. None of it would ever develop multicellularity, nervous systems, intelligence, or technology. The universe could be teeming with life, and yet utterly devoid of minds. A cosmos of slime, with no one to appreciate its grandeur. There is another chemical obstacle that deserves attention, one that is often overlooked in popular discussions, but is taken seriously by astrobiologists. Life as we know it. All life on Earth requires 6 key elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Of these 6, phosphorus stands out as the odd one. Carbon, hydrogen, nitrogen, and oxygen are among the most abundant elements in the universe. Sulfur is reasonably common, but phosphorus is relatively scarce. It is produced primarily in the cataclysmic death throes of massive stars, in supernovae, and in a specific type of stellar explosion known as an oxygen neon nova. Its distribution across the galaxy is uneven. Some regions may have abundant phosphorus, others may be severely depleted. And phosphorus is not optional for life. It is the backbone of DNA and RNA. It is essential for ATP, the molecule that serves as the energy currency of all living cells. Without phosphorus, there is no genetic code, no energy metabolism, no life as we know it. NASA-funded research has shown that phosphorus was extremely scarce in Earth's ancient oceans for extended periods, and this scarcity may have constrained the development of early life. If many habitable planets and other star systems lack sufficient phosphorus in their crusts and oceans, then even if all other conditions are perfect, life may simply never get started. The right temperature, the right amount of water, the right atmospheric composition, all of it would be irrelevant without this one critical element. So we have already identified 2 massive potential barriers to the emergence of complex, intelligent life. Abiogenesis itself might be extraordinarily rare, and even if simple life is common, the transition from simple prokaryotic cells to complex eukaryotic cells might be a nearly impossible evolutionary leap that almost never occurs. But the chain of improbability does not stop there. Even after eukaryotes appeared on Earth, the road to intelligence was long, winding, and punctuated by catastrophes that nearly ended the experiment altogether. Eukaryotic cells appeared roughly 2 billion years ago, Multicellular life did not fully diversify until roughly 600 million years ago, during the Ediacaran period and the subsequent Cambrian explosion. That is, a gap of approximately 1.4 billion years between the appearance of complex cells and the appearance of complex animals. 1.4 billion years of eukaryotes existing without producing anything more sophisticated than simple colonial organisms and early multicellular forms. Why so long? One critical enabling factor was the development of sexual reproduction, which appeared roughly 1.2 billion years ago. Sexual reproduction, unlike asexual reproduction, shuffles genetic material between individuals, creating enormous genetic diversity within a population. This diversity is the raw material of evolution. Without it, adaptation is slow and limited. With it, evolution can explore a vast landscape of possible forms and functions. Sexual reproduction accelerated the pace of evolutionary innovation. But even with this engine of diversity running, complex animal life did not appear for another 600 million years. The evolution of multicellularity, of differentiated tissues, of nervous systems, of coordinated animal behavior, all of this took time, immense amounts of time. And during that time, something else was happening, something that fundamentally reshaped the planet and every living thing on it. Roughly 2.4 billion years ago, photosynthetic prokaryotes that had been quietly producing oxygen as a waste product for hundreds of millions of years finally tipped the balance of Earth's atmosphere. Oxygen levels began to rise dramatically in what is known as the Great Oxidation Event, sometimes called the oxygen catastrophe. I call your attention to that second name, catastrophe, because for the organisms alive at the time, which had evolved in an oxygen-free environment, the rising oxygen levels were lethal. Oxygen is a highly reactive molecule. It destroys the biochemical machinery of organisms that are not adapted to it. The Great Oxidation Event is believed to have caused one of the most severe mass extinctions in Earth's history, wiping out a vast proportion of anaerobic life. But from this catastrophe arose opportunity. Organisms that could tolerate or exploit oxygen had access to a far more efficient energy metabolism. Aerobic respiration extracts much more energy from food than anaerobic processes. This energy surplus would eventually fuel the development of large, active, complex organisms, including animals. The catastrophe that nearly ended life also made complex life possible. This is a pattern we will see again and again. Destruction creating the conditions for advancement. The Cambrian explosion, roughly 538 million years ago, is one of the most dramatic events in the history of life. Over a relatively brief period of perhaps 20 to 25 million years, nearly all major animal body plans appeared in the fossil record. Animals with eyes, shells, legs, claws, nervous systems, brains. An explosion of biological innovation that transformed the oceans from a world of simple organisms into a complex ecosystem of predators and prey. But notice something important. None of these animals were intelligent in any meaningful sense. They were sophisticated, yes. They had complex behaviors, but none of them could use tools, create art, develop language, or build technology. And this state of affairs, complex animal life without technological intelligence, persisted for over 500 million years. During those 500 million years, life on Earth endured 5 massive extinction events, each of which nearly reset the entire experiment. The first was the end Ordovician extinction, roughly 445 million years ago. Earth's climate cooled dramatically, glaciers advanced, sea levels dropped, and approximately 85% of all marine species perished. Life recovered, but the recovery took millions of years. The second was the late Devonian extinction, roughly 372 million years ago. The causes are still debated, but ocean anoxia, the depletion of oxygen in seawater, played a central role. Approximately 75% of all species were lost. The third, and by far the worst, was the Permian-Triassic extinction, roughly 252 million years ago. Known as the Great Dying, this event killed approximately 96% of all marine species and 70% of all land-based vertebrate species. The cause is believed to have been massive volcanic eruptions in what is now Siberia, known as the Siberian Traps, which released enormous quantities of carbon dioxide and other gases, triggering runaway global warming, ocean acidification, and oxygen depletion. Life came within a hair's breadth of being extinguished entirely. The planet took roughly 10 million years to recover. The fourth was the end Triassic extinction, roughly 201 million years ago, again linked to massive volcanism, which eliminated approximately 80% of species and cleared the way for the rise of the dinosaurs. And the fifth was the end Cretaceous extinction, roughly 66 million years ago, caused by the impact of an asteroid approximately 10 kilometers in diameter that struck what is now the Yucatan Peninsula in Mexico. This event killed approximately 76% of all species, including all non-avian dinosaurs. That last extinction deserves special attention because it is directly relevant to the question of why we are here and whether intelligence is an inevitable product of evolution. Dinosaurs dominated Earth for approximately 165 million years. 165 million years. For context, the entire genus Homo, including all human species that have ever existed, has been around for roughly 2 to 3 million years. Modern Homo sapiens have existed for about 300,000 years. Dinosaurs had a head start on us of over 160 million years, and in all that time, none of them developed technology, none of them developed language, mathematics, or science. They were successful. They were diverse. Some of them, like the troodontids, were relatively brainy for their time, but none of them crossed the threshold into what we would recognize as intelligence. If the asteroid had not struck 66 million years ago, dinosaurs would likely still be the dominant land animals on Earth, and there is no reason to believe they would have ever developed civilization. Mammals, which had existed alongside the dinosaurs for over 100 million years, as small, nocturnal, mostly inconspicuous creatures, would probably still be hiding in the shadows. The entire chain of mammalian evolution that led to primates, to apes, to hominids, to Homo sapiens, was only possible because an asteroid happened to hit the right planet at the right angle at the right time. If it had arrived a few million years earlier or later, if it had struck an ocean instead of a shallow sea over a sulfur-rich geological formation that maximized the climatic damage, the extinction might not have been severe enough to unseat the dinosaurs, and we would not exist. Your existence, my existence, the existence of everyone and everything we call human civilization may ultimately depend on a rock from space that happened to be in the wrong place at the wrong time 66 million years ago. This leads to a profound and uncomfortable observation about the nature of intelligence. A 2025 article in Quanta magazine confirmed what many evolutionary biologists have long suspected. Intelligence, at the level of complex problem solving, has evolved multiple times independently. Birds, particularly corvids like crows and ravens, have evolved remarkably sophisticated cognitive abilities independently from mammals. Octopuses have evolved complex problem solving, and even tool use on a completely separate evolutionary branch. Dolphins and whales have evolved large, complex brains independently from primates. So at a basic level, intelligence does appear to be something that evolution produces repeatedly. But there is an enormous crucial distinction between problem-solving intelligence and technological civilization-building intelligence. Crows can use tools. Octopuses can open jars. Dolphins can communicate in sophisticated ways. None of them have built a radio telescope. None of them have developed writing, mathematics, or agriculture. None of them have harnessed fire, smelted metal, or split the atom. In 4 billion years of life on Earth, encompassing an estimated 1 billion total species that have ever lived, exactly one species has developed the kind of intelligence that can detect exoplanets and wonder about the Fermi Paradox. 1 out of a billion. And that species, Homo sapiens, has existed for only about 300,000 years. We have had agriculture for about 12,000 years. We have had writing for about 5,000 years. We have had science for about 400 years. We have had radio technology for about 130 years. We have had the ability to send and detect signals across interstellar distances for perhaps 100 years. 100 years out of 4 billion. If you compressed the entire history of life on Earth into a single 24-hour day, human technological civilization would occupy the last 0.2 seconds. Less than the blink of an eye. Technological intelligence may not be just rare, it may be evolution's single most improbable product. A freak. An aberration. A 1 in a billion accident that happened to occur on one planet, around one star, in one galaxy. And if that is the case, the silence of the cosmos is not surprising at all. It is exactly what you would expect. But we are not done yet, because even if a species manages to beat all of those odds, even if life arises, complex cells evolve, multicellular organisms develop, intelligence emerges, and a civilization builds technology capable of communicating across the stars, there remains one more filter, and this one might be the most chilling of all, because this one is not about the difficulty of evolution or the rarity of chemistry. This one is about the tendency of intelligent species to destroy themselves. Think about what happens when a civilization develops advanced technology. The same technology that allows you to communicate across a planet also allows you to wage war across a planet. The same technology that allows you to harness nuclear energy also allows you to build nuclear weapons. The same industrial processes that fuel economic growth also drive climate change. The same biological knowledge that produces vaccines also makes engineered pandemics possible. The same artificial intelligence that can solve complex problems could, if misaligned with human values, pose existential risks. Technology is a double-edged sword, and history suggests that civilizations tend to develop destructive capabilities faster than they develop the wisdom to manage them. Humanity has had nuclear weapons since 1945. That is 81 years. In that time, we have come terrifyingly close to nuclear war on multiple occasions. The Cuban Missile Crisis in 1962, the 1983 Soviet nuclear false alarm incident, when a Soviet satellite erroneously detected incoming American missiles, and only the judgment of a single officer, Stanislav Petrov, prevented a retaliatory launch. The Able Archer 83 NATO exercise, which the Soviet Union nearly interpreted as cover for a real first strike. We have survived these close calls, so far. But a study published in 2025 showed that the detonation of just 2% of the world's current nuclear arsenal on cities would be sufficient to create ice age temperatures globally, putting over 2 billion people at risk of starvation. 2%. The destructive capacity we possess is almost beyond comprehension. And nuclear weapons are just one of several existential threats. Climate change, driven by the burning of fossil fuels, is altering Earth's climate at a rate that is unprecedented in the geological record. The global average temperature has already risen by more than 1 degree Celsius since the pre-industrial era, and the trajectory, without dramatic intervention, points toward warming of 2 to 4 degrees or more by the end of this century. This may not sound like much, but it is enough to destabilize ecosystems, raise sea levels, intensify extreme weather, disrupt agriculture, and trigger resource conflicts. Engineered pandemics, made possible by advances in synthetic biology, represent another category of existential risk. The development of increasingly sophisticated artificial intelligence raises questions about alignment and control that the scientific community is only beginning to grapple with. And all of these threats are emerging simultaneously within a span of just a few centuries. Here is the key question. Is this pattern, the development of self-destructive technology, universal? Does every intelligent civilization on every planet inevitably develop the means to destroy itself before it develops the means to spread beyond its home world? We obviously cannot answer this question with certainty because we have a sample size of 1. But the logic is suggestive. The development of nuclear physics seems likely to follow naturally from the development of basic science. The development of industrial chemistry seems likely to lead to atmospheric pollution. The development of biology seems likely to enable engineered pathogens. These are not arbitrary choices. They follow from the structure of physical law. Any civilization that develops science will discover nuclear physics. Any civilization that industrializes will burn fuel and alter its climate. The tools of creation and the tools of destruction are often the same tools. Research published in 2025 and 2026 has attempted to estimate the average lifespan of a technological civilization. A 2026 study, discussed in the science news outlet phys.org, under the headline, "How long do civilizations last?" examined this question in detail and concluded that humanity has been a technological civilization, in any meaningful sense, for only about 200 years, and that we are statistically at the very beginning of whatever our lifespan will be. A related paper published in the Archive preprint repository in 2025 analyzed the constraints on civilization lifetimes and concluded that if intelligent life is common in the galaxy, then technological civilizations must be relatively short-lived. The reasoning is straightforward. If civilizations commonly survived for millions of years, some of them would have colonized the galaxy by now, and we would see evidence of them. The fact that we do not see such evidence places an upper limit on how long civilizations typically last. Another estimate, based on astronomical modeling and reported by the science outlet Gizmodo, suggested that the average lifespan of a technologically advanced civilization might be on the order of just 5,000 years. 5,000 years. That is roughly the age of the Egyptian pyramids. If this estimate is correct, then civilizations are like fireflies. They flicker on, shine briefly in the cosmic darkness, and then go out. The window during which a civilization is both technologically active and not yet destroyed is so narrow, on cosmic timescales, that the probability of two such civilizations existing simultaneously and close enough to detect each other is vanishingly small. All of these individual observations, the potential rarity of abiogenesis, the improbability of eukaryogenesis, the difficulty of evolving technological intelligence, the tendency towards self-destruction, were brought together in 1996 by an economist named Robin Hanson in a concept that has become one of the most important ideas in astrobiology. Hanson called it the Great Filter. The Great Filter is not a specific event. It is a concept. It represents whatever barriers stand between lifeless matter and a galaxy-spanning civilization. Hanson proposed that to go from a dead planet to a civilization that colonizes the stars, a species must pass through a series of critical steps. He listed several. A habitable planet must form in a star's habitable zone. Reproductive molecules like DNA and RNA must arise. Simple, single-celled life must develop. Those simple cells must evolve into complex eukaryotic cells. Multicellular organisms must emerge. Sexual reproduction must develop. Tool-using intelligent organisms must evolve. Those organisms must develop advanced technology capable of space colonization. And finally, they must actually colonize space without destroying themselves first. Each of these steps has some probability of occurring, and at least one of them, Hanson argued, must have an extremely low probability. Otherwise, given the age and size of the galaxy, civilizations would be everywhere, and the silence would be inexplicable. As Hanson wrote, there exists a great filter between death and expanding lasting life, and humanity faces the ominous question, how far along this filter are we? This question, whether the great filter lies behind us or ahead of us, is not just an academic exercise. It has profound implications for the future of humanity. If the great filter is behind us, if one of the earlier steps, like abiogenesis or eukaryogenesis, is the nearly impossible hurdle, then we have already cleared it. We are special. We are rare. We may be the only civilization in the galaxy, or one of very few, and the future is open to us. This is, in a strange way, the optimistic scenario. The silence of the cosmos would be a sign that we are extraordinary, that the chain of events that produced us is so improbable that it has not been replicated anywhere else in the observable universe. But if the great filter is ahead of us, if the nearly impossible hurdle is something we have not yet encountered, then we are in deep trouble. It would mean that many civilizations before us have reached our level of development and then been destroyed or permanently arrested by some catastrophe that we have not yet faced. Nuclear war, climate collapse, a technological disaster we cannot foresee, an artificial intelligence that turns against its creators, a biological weapon that escapes containment, something that has killed every civilization that has ever reached this point. And we would be next. This is why some scientists have made a statement that sounds paradoxical on its surface, but makes perfect sense in the context of the Great Filter. They say, the best possible news we could receive is that Mars is completely, utterly dead. Sterile. No life whatsoever. This sounds counterintuitive. Why would we want Mars to be dead? Because if Mars has life, especially if Mars has complex life, it would mean that the early steps in the Great Filter are not the bottleneck. If life arose independently on both Earth and Mars, two planets in the same solar system, it would strongly suggest that abiogenesis is easy, that life arises readily wherever conditions allow. And if life is easy, then the filter must be somewhere later in the sequence. It must be something that happens to civilizations after they develop, not before. It must be ahead of us. So finding life on Mars, far from being hopeful, would actually be terrifying. It would mean we are probably not special. It would mean many civilizations have gotten to where we are. And it would mean something ahead of us is killing them all. There is also the possibility that there is no single great filter, but rather a series of moderately difficult filters, what you might call death by 1,000 cuts. Perhaps each step in the chain has a relatively low but not impossibly low probability. Maybe the chance of abiogenesis on a habitable planet is 1 in 100. Maybe the chance of eukaryogenesis is 1 in 100. Maybe the chance of intelligence is 1 in 100. Maybe the chance of surviving the first few centuries of technology is 1 in 100. Individually, none of these hurdles is insurmountable. But multiply them together. 1 in 100 times, 1 in 100 times, 1 in 100 times, 1 in 100 equals 1 in 100 million. And that is just 4 hurdles. If there are 9 steps in the chain and each has even a 1 in 10 probability, the cumulative probability is 1 in a billion. This multiple filters scenario does not require any single step to be almost impossible. It just requires a series of moderately difficult steps, and the math takes care of the rest. The result is the same. Civilizations almost never complete the full sequence. Now, I want to turn to a category of explanation that moves away from biology and evolution and into the realm of astrophysics, because the universe is not just passively difficult for life. In some ways, it is actively hostile, and there are events in the cosmos that could wipe out a civilization instantly, without warning, and without any possibility of defense. The most terrifying of these are gamma-ray bursts. A gamma-ray burst is the most powerful type of explosion in the universe, second only to the Big Bang itself. There are 2 types. Short gamma-ray bursts, lasting less than 2 seconds, are caused by the merger of 2 neutron stars or a neutron star and a black hole. Long gamma-ray bursts, lasting from a few seconds to several minutes, are caused by the collapse of a massive star into a black hole. In both cases, an inconceivable amount of energy is released in a narrow beam. If Earth happened to be in the path of such a beam from a relatively nearby source, within about 6,500 light-years, the results would be catastrophic. The burst of gamma radiation would strip away a significant portion of the ozone layer, exposing all surface life to lethal levels of ultraviolet radiation from the sun. Photosynthesis in the oceans would collapse. The food chain would disintegrate. A mass extinction would follow. And the most chilling aspect, there would be no warning. Gamma-ray bursts travel at the speed of light. The first sign of the burst would be the burst itself. By the time you saw it, it would already be over. Some scientists have suggested that a gamma-ray burst may have been responsible for the end Ordovician mass extinction 445 million years ago, though this remains speculative. What is not speculative is that gamma-ray bursts were far more common in the early universe, when the galaxy was younger and denser, and the rate of star formation and stellar death was much higher. In the first several billion years of the Milky Way's history, gamma-ray bursts may have been frequent enough to sterilize large portions of the galaxy repeatedly, preventing life from gaining a foothold, or, if it did, destroying it before it could develop complexity. Only as the galaxy aged and the rate of catastrophic stellar events decreased did the environment become calm enough for complex life to persist long enough to evolve intelligence. We may live in one of the first windows of cosmic history in which advanced life is even possible. Supernovae, the explosive deaths of massive stars, represent a related but less extreme threat. A supernova within roughly 30 light-years of Earth could cause significant damage to the ozone layer and trigger elevated cancer rates and ecological disruption. The galactic center, where stars are densely packed and supernovae are relatively frequent, is likely hostile to the long-term survival of complex life. Only stars in the outer disk of the galaxy, in what scientists call the galactic habitable zone, are far enough from the center to avoid frequent sterilization. Our Sun happens to sit in this zone, between roughly 7 and 9 kiloparsecs from the galactic center. This is another item on the long list of conditions that make Earth unusual. Asteroid and comet impacts are another form of cosmic Russian roulette. The end Cretaceous impact 66 million years ago demonstrates what a single large asteroid can do. But Earth has been partially protected from such impacts by an unusual feature of our solar system, Jupiter. Jupiter's enormous gravitational field acts as a kind of cosmic vacuum cleaner, attracting and deflecting many asteroids and comets that might otherwise rain down on the inner planets. Studies suggest that without Jupiter, the rate of major impacts on Earth would be significantly higher, potentially too high for complex life to persist. Not all planetary systems have a Jupiter analogue. Many do not. Those planets may be bombarded too frequently for life to develop beyond the microbial stage. These astrophysical threats are real, documented, and well understood. They represent filters that operate independently of anything a civilization does. A gamma-ray burst does not care how advanced your technology is. An asteroid does not check whether you have achieved interstellar travel. These are blind, random, impartial destroyers, and they could wipe out a developing civilization at any stage, without warning and without recourse. Now, I want to address a category of hypothesis that is different from the others, one that does not assume we are alone, but rather that the universe is full of life, and the silence is deliberate. This is the dark forest hypothesis, and it is, to many people, the most psychologically disturbing of all the proposed explanations for the Fermi Paradox. The dark forest hypothesis was most famously articulated by Chinese science fiction author Liu Cixin in his novel The Dark Forest, the second book in his Remembrance of Earth's Past trilogy. But the idea has been discussed independently by multiple scientists and philosophers, and it has a logical structure that is disturbingly rigorous. The hypothesis is built on two axioms. First, survival is the primary need of every civilization. Second, civilizations continuously grow and expand, but the total amount of matter and energy in the universe remains constant. From these two axioms, combined with two additional observations, you can derive the dark forest conclusion. The first observation is the chain of suspicion. Because interstellar distances are so vast and communication takes so long, you can never be truly certain of another civilization's intentions. Even if they claim to be peaceful, you have no way to verify this, and they have no way to verify your intentions either. This mutual uncertainty is irreducible. The second observation is the concept of technological explosion. A civilization's technology can advance very rapidly and unpredictably. A civilization that seems primitive and harmless today could, within a cosmically insignificant span of a few centuries, become overwhelmingly powerful. You cannot judge a civilization's future capability by its current state. Combine all of this, and you arrive at the dark forest conclusion. The safest strategy for any civilization in the universe is to remain completely silent and, if you detect another civilization, to destroy it immediately before it can become a threat. Because you cannot know its intentions and you cannot predict how powerful it will become, the only rational strategy is preemptive elimination. The universe, under this hypothesis, is like a dark forest at midnight. Every civilization is a hunter, creeping silently through the trees, rifle raised, terrified of every sound. If you see another hunter, you shoot first, because the cost of hesitation might be extinction. The silence of the cosmos, under this interpretation, is not the silence of an empty forest. It is the silence of a forest full of predators, each one frozen in place, listening, waiting, hiding. Now, I want to be clear, the dark forest hypothesis is a hypothesis. It is not a proven theory. It has significant criticisms. It assumes that all civilizations are paranoid and that the default interaction between civilizations is hostile, which may not be the case. It assumes that destruction is easy and communication is dangerous, which may not be true. It ignores the potential for cooperation, mutual benefit, and the shared advantages of contact. Some scientists argue that a sufficiently advanced civilization would have no reason to fear a less advanced one, and could easily defend itself without resorting to preemptive destruction. Others point out that the hypothesis relies on game theory assumptions that might not apply to truly alien minds with truly alien values. But the dark forest hypothesis has a quality that makes it difficult to dismiss entirely. Its logic is internally consistent. If you grant the axioms, the conclusion follows, and it offers a terrifying explanation for why broadcasting your location into the cosmos might be the most dangerous thing a civilization can do. Humanity has been broadcasting radio signals into space for about 100 years. Our signals, traveling at the speed of light, have now reached stars up to 100 light-years away. That sphere of radio emissions, expanding outward from Earth at the speed of light, is sometimes called our radio bubble. It encompasses several thousand stars. Now, in reality, our unintentional radio leakage, the signals from television broadcasts, radar installations and cellular networks, is extremely weak by the time it reaches even the nearest stars. It would be very difficult for an alien civilization to detect these signals, unless they had far more sensitive equipment than anything we possess. But deliberate, focused transmissions, like the Arecibo message beamed toward the globular cluster M13 in 1974, are a different matter. Those are powerful, narrow, and clearly artificial. If the dark forest hypothesis is correct, sending such messages is the cosmic equivalent of lighting a bonfire in a forest full of wolves. Whether this concern is justified is a matter of intense debate among scientists. The probability may be extremely low, but the stakes, the potential extinction of our entire species, are infinitely high. And when the stakes are infinite, even a small probability demands serious attention. A related but even darker concept is the Berserker hypothesis. Named after Fred Saberhagen's science fiction series, this hypothesis proposes that the galaxy may contain self-replicating machines, von Neumann probes that had been reprogrammed or designed from the beginning to seek out and destroy emerging civilizations. Perhaps they were created billions of years ago by a now extinct civilization during a war that escalated beyond control. Perhaps they were designed as a weapon against a specific enemy, but continued to operate long after their creators were gone. Perhaps they are the product of an artificial intelligence that decided for its own reasons that biological civilizations are threats to be eliminated. These berserker probes would roam the galaxy endlessly, replicating themselves from the raw materials of asteroid belts and planetary crusts, guided by sensors that detect the electromagnetic signatures of developing civilizations. When they find one, they destroy it. Under this hypothesis, the silence is not because civilizations never arise. They do arise, perhaps frequently, but they are hunted, they are found, and they are eliminated before they can spread. This is highly speculative. There is no evidence for the existence of berserker probes, but the concept is discussed seriously in the scientific literature because it is physically plausible. Self-replicating machines are not forbidden by any law of physics. If they existed, they could indeed explore and sterilize the galaxy within a few million years. The absence of evidence is not evidence of absence, especially when the hypothesis predicts that we would see no evidence, because any civilization that might have provided it has already been destroyed. There are also hypotheses that suggest we are not alone but simply cannot perceive our cosmic neighbors. The zoo hypothesis, proposed by John Ball in 1973, suggests that advanced extraterrestrial civilizations are aware of humanity but have deliberately chosen not to interfere, treating Earth as a kind of nature preserve or wildlife sanctuary. Under this hypothesis, we are being observed but not contacted, much as humans might observe animals in a protected wilderness without revealing their presence. The idea has a certain appealing logic, but it faces a critical objection. It requires a galactic consensus. Every civilization, without exception, would need to agree to the non-interference policy. Even one rule breaker, one civilization or individual that decided to make contact, would shatter the zoo. The probability of such perfect universal compliance seems low, especially given what we know about the diversity of motivations even within a single species. The Soviet rocket scientist Konstantin Tsiolkovsky proposed something similar in the 1930s, suggesting that advanced aliens had quarantined humanity to allow for independent cultural development. But the objection remains the same. A quarantine works only if everyone enforces it. Another intriguing possibility is that alien civilizations are communicating, but using methods we cannot detect. Our search for extraterrestrial intelligence has focused overwhelmingly on radio and optical signals, electromagnetic radiation that we know how to generate and detect. But electromagnetic communication is, in the grand scheme of physics, a relatively primitive technology. Advanced civilizations might communicate using neutrino beams, gravitational waves, quantum entanglement, or technologies based on physics we have not yet discovered. If this is the case, our SETI searches are like listening for smoke signals in an era of fiber optic internet. We are searching in the wrong medium entirely. The 2025 SETI Institute finding that stellar plasma turbulence could blur radio signals adds another layer to this concern. Even if civilizations are broadcasting via radio, natural astrophysical processes might be degrading their signals to the point of undetectability. We might be surrounded by a conversation we cannot hear. Now, I have walked you through the major categories of explanation for the Fermi Paradox. Life might be rare, complex life might be rarer, intelligence might be rarest of all. Civilizations might destroy themselves. Cosmic events might destroy them from outside. The universe might be a dark forest where silence is survival. Berserker probes might hunt down any civilization that reveals itself. Advanced civilizations might be hiding, observing, or communicating in ways we cannot detect. Each of these hypotheses addresses the silence from a different angle. Each has strengths and weaknesses. Each is supported by some evidence and challenged by other evidence. But I believe that the most chilling explanation, the one that should keep you up at night, is not any single one of these hypotheses in isolation. It is the convergence of all of them into a single, unified picture. Let me paint that picture for you now. Imagine the universe as an enormous obstacle course, not a single wall to climb, but a gauntlet, a long series of barriers, each one difficult, each one potentially lethal, stretching from the formation of a planet to the colonization of the stars. The first barrier is getting the right planet. Not just any planet in a habitable zone, but a planet with the right mass, the right composition, the right amount of water, the right magnetic field, plate tectonics, a stabilizing moon, a protective gas giant in the outer solar system, located in the galactic habitable zone, orbiting a stable, long-lived star. Each of these conditions individually might not be extremely rare, but the combination of all of them is. Earth may not be unique, but it is unusual. The second barrier is abiogenesis. Even on a perfect planet, life must somehow arise from non-living chemistry. This may happen readily, or it may be a 1 in a trillion cosmic lottery. We do not know. The third barrier is the leap from simple prokaryotic cells to complex eukaryotic cells. On Earth, this took 2 billion years and happened exactly once. The universe might be full of bacterial worlds and empty of anything more complex. The fourth barrier is the evolution of multicellularity, sexual reproduction, and complex animal body plans. This requires hundreds of millions of years of relatively stable conditions, free from sterilizing catastrophes like gamma-ray bursts or massive asteroid impacts. The fifth barrier is the evolution of intelligence, specifically the kind of technological intelligence that can build civilizations. In 4 billion years of life on Earth, this has happened exactly once, in one species very recently. The sixth barrier is surviving your own technology, developing nuclear weapons, industrial pollution, biological engineering, and artificial intelligence without destroying yourself in the process. We are currently in the middle of this test, and we have no idea whether we will pass it. And the seventh barrier, if the dark forest or berserker hypotheses have any truth to them, is that even if you survive everything else, there might be something out there actively hunting for you. Each barrier reduces the number of civilizations that make it through. If each step has even a moderate probability of failure, the cumulative probability of any civilization completing the entire gauntlet and becoming a galaxy-spanning species is effectively zero. Not low, not improbable. Effectively zero. And that is the most chilling explanation for the silence. It is not that one thing is impossible. It is that the entire path is so long, so difficult, and so fraught with potential failure at every step, but almost nothing completes it. The universe is not empty because there is one wall that blocks everyone. It is empty because there is a gauntlet of 100 walls, and surviving all of them, in sequence, without failing at any one, is almost impossible. Let me now bring this home with a concrete example. Our own planet. The story of Earth is the most detailed case study we have of how a planet can navigate this gauntlet, and it reads like a miracle when you examine it closely. 4.6 billion years ago, in a quiet arm of the Milky Way, in the galactic habitable zone, a cloud of gas and dust collapsed under its own gravity and formed a new star, our Sun. Around it swirled a disk of leftover material that gradually coalesced into planets. The third planet from the Sun, Earth, formed at just the right distance, where liquid water could exist on the surface. Not too close like Venus, where a runaway greenhouse effect would boil the oceans. Not too far like Mars, where the thin atmosphere would freeze them. But just right. Roughly 100 million years after Earth formed, something extraordinary happened. A Mars-sized body, which scientists have named Theia, collided with the young Earth in a cataclysmic impact. The collision was so violent that it partially melted both bodies and ejected an enormous amount of material into orbit around Earth. That material gradually coalesced into the Moon. Our Moon is unusually large relative to its planet. It is the largest moon relative to its host planet of any major body in our solar system, and it plays a critical role in making Earth habitable. The Moon's gravitational influence stabilizes Earth's axial tilt at approximately 23.5 degrees. Without the Moon, Earth's tilt would wobble chaotically over millions of years, swinging from nearly 0 degrees to as much as 85 degrees. Such extreme variations would cause radical climate swings, with the poles alternately baking in permanent sunlight and the equator freezing under permanent shadow. Complex life would likely be impossible under such conditions. The Moon also drives the tides, which may have played a role in the chemistry of life's origin by creating tidal pools where organic molecules could concentrate and interact. The Theia impact was a random event. It did not have to happen, and without it, we would almost certainly not be here. Earth also has a powerful magnetic field generated by the convective motion of liquid iron in its outer core. This magnetic field creates a magnetosphere that deflects the solar wind, a constant stream of charged particles flowing outward from the sun. Without this magnetic shield, the solar wind would gradually strip away Earth's atmosphere, as it did to Mars. Mars once had a thicker atmosphere and liquid water on its surface, but its smaller size caused its core to cool and solidify, its magnetic field to dissipate, and its atmosphere to be slowly eroded by the solar wind over billions of years. Earth's larger size and more geologically active interior kept its core molten, its magnetic field strong, and its atmosphere intact. This is not guaranteed for all rocky planets. Earth also has plate tectonics, the slow but ceaseless movement of the planet's crustal plates. Plate tectonics is driven by the heat in Earth's interior and plays several crucial roles in maintaining habitability. It recycles carbon by subducting carbon-bearing rocks into the mantle and releasing carbon dioxide through volcanic eruptions, maintaining a long-term carbon cycle that regulates the planet's temperature. Without plate tectonics, Earth might have experienced a runaway greenhouse effect, like Venus, or a permanent snowball state. Plate tectonics also creates diverse environments, mountains, valleys, ocean trenches, volcanic islands that drive evolution by creating ecological niches. And it refreshes the planet's surface, bringing up fresh minerals and nutrients that sustain biological productivity. Not all rocky planets have plate tectonics. Many may have stagnant lids, a single solid crust that does not move, leading to geological and climatic stagnation. Far out in the solar system, Jupiter and Saturn, the two largest planets, serve as gravitational sentinels. Their massive gravitational fields perturb the orbits of asteroids and comets, deflecting many away from the inner solar system. Jupiter, in particular, has been described as Earth's cosmic bodyguard, reducing the rate of catastrophic impacts to a level that allows complex life to persist and evolve. Without Jupiter, Earth might be bombarded so frequently that complex life would be repeatedly destroyed before it could develop intelligence. Many exoplanetary systems discovered so far do not have a Jupiter analogue or have gas giants in very different orbits that might not provide this protective effect. Add all of these factors together, and you begin to see why the rare Earth hypothesis, proposed by geologist Peter Ward and astronomer Donald Brownlee in 2000, has gained significant scientific traction. Their argument is that while simple microbial life might be common in the universe, the specific combination of factors that allowed complex, intelligent life to develop on Earth, the right star, the right planet, the right moon, the right magnetic field, the right plate tectonics, the right location in the galaxy, the right cosmic bodyguard, the right sequence of catastrophes and recoveries, is so extraordinarily unlikely that it may have occurred only once, or at most a handful of times, in the entire Milky Way. After Earth's formation and the creation of the Moon, the planet endured the late heavy bombardment, a period roughly 4.1 to 3.8 billion years ago, during which the inner solar system was pummeled by asteroids. The bombardment was probably triggered by a gravitational reshuffling of the giant planet's orbits. Enormous impacts repeatedly sterilized portions of Earth's surface and may have boiled away portions of the oceans. But Earth's mass was large enough and its oceans deep enough that some environments, particularly deep-sea hydrothermal vents, may have remained habitable throughout the bombardment. And, remarkably, almost immediately after the bombardment subsided, the first signs of life appeared in the fossil record. Whatever process gave rise to life was either extremely fast or had already been underway during the bombardment itself, with life sheltering in protected environments. For the next 2 billion years, roughly from 3.8 billion years ago to about 1.8 billion years ago, Earth was a world of microbes. Prokaryotic cells, bacteria, and archaea were the only life forms. They were successful, they were diverse, they were ecologically dominant, but they were simple. They did not form tissues or organs. They did not develop nervous systems. They existed in a state of biological stasis, with incremental evolutionary changes but no quantum leaps in complexity. During this period, however, something was slowly changing. Cyanobacteria, a group of photosynthetic prokaryotes, had evolved the ability to split water molecules using sunlight, releasing oxygen as a waste product. For hundreds of millions of years, this oxygen was absorbed by dissolved iron in the oceans and by minerals on the land surface. But eventually, these oxygen sinks were saturated. Around 2.4 billion years ago, oxygen began to accumulate in the atmosphere. This was the Great Oxidation Event. For the anaerobic organisms that had dominated Earth for over 1 billion years, the rising oxygen was poison. It destroyed their biochemistry and drove many of them to extinction, or into oxygen-free refuges deep underground and in stagnant sediments. The Great Oxidation Event was, for the existing biosphere, a catastrophe on a scale that dwarfs any of the later mass extinctions. But it also opened a door. Organisms that could tolerate or exploit oxygen had access to a vastly more efficient form of energy production. Aerobic respiration, the process by which oxygen is used to metabolize food, produces roughly 18 times more energy per unit of glucose than anaerobic processes. This energy surplus was a prerequisite for the evolution of large, active, complex organisms. Without the Great Oxidation Event, complex life would likely never have evolved. The catastrophe was also an opportunity. The worst event in Earth's biological history was simultaneously the best thing that ever happened to the future of complexity.